In this video lecture, I will have a look at the assumptions underlying factor models. So far, actually, there's nothing here which tells us, except that R should be small, how factors are separate from idiosyncratic components. So this is going to be, of course, a major part of what a factor model means, right? We need to have something which is actually common and something which is idiosyncratic. Well, one harmless assumption we make is that our idiosyncratic components have mean zero. Again, you could simply absorb that into an intercept if you would want to. Now we're also going to assume for now that our idiosyncratic components are actually going to be IID, just to simplify the expressions a bit. And so the key assumption that we assume, or one of the key assumptions in factor models, is that there's no correlation between f and mu. So they should really be orthogonal, the factors, to the idiosyncratic components in order to be properly able to distinguish the two. Regarding the idiosyncratic components among each other, there we can be a bit more relaxed. So of course, one thing you could assume is that the idiosyncratic component is independent over all variables. And if you have that case, or in particular if you have the case of no correlation, we have exact factor models. Now this is going to be very restrictive, obviously, because it means that all the correlation between different variables in X must go through F. And there's only commonality, and there's nothing, for instance, neighbors who might be correlated through the idiosyncratic components. So to weaken this, we want to look at approximate factor models, and for that we allow some form of dependence in our idiosyncratic components across cross-section, across the number of variables. In particular, what we need is that this double sum, when divided by p, is smaller than infinity. Now this looks very similar to actually a time series setup where we would define weak dependence in a very similar way. So essentially what this tells us is that there is some dependence allowed. For instance, if x1 and x2 are, for whatever reason, very closely related, we can allow only those two to be related through the idiosyncratic component, but it should not persist through all variables, because if it did, then it would actually be a factor. So what we have is that the factor should absorb all strong correlations. So correlations that don't die out if you move further away between series, in whatever way we define further away, because obviously there's no natural ordering of variables. But the only source of strong correlation that persists throughout the system should be the factor. So we can have a look, for instance, at an example of whether what could be or could not be allowed. So take a setting where the correlation between all units j and j prime, variables j and j prime, is equal to rho. So we get a 1, of course, diagonal. We assume a variance of 1 and a correlation of rho for all variables. Now we can then, of course, derive this double sum. Well, you can split it then into the sum of the variances and the covariances. Well, you have p variances, so this becomes a sum of order p. But you have p times p minus 1 covariances. So here we get a sum of order p squared. So clearly, if we divide that by p, which is what we should have, and then be finite, this will not work because p squared increases too fast. So here we have a case that if all the variables are equally correlated, that actually does not fit into your idiosyncratic components. So you might worry about that because it might not seem such a bad case. I mean, we've already looked, for instance, at this where the variables all have equal correlation. Does that rule out factors? Well, maybe we should reconsider what we think of as factors. So for instance, if you would write things out for this case, then suppose that our factors have a certain covariance matrix, sigma f. Our idiosyncratic components have a certain covariance matrix, sigma v. And we assume that there is no correlation between f and v, because we want to assume that the factors are really orthogonal to the idiosyncratic components. then, and this is a very common expression in factor models, and we'll also see that later on used in when we look at covariance matrix estimation, we can write the covariance matrix of our axis as a sum of a covariance matrix consisting only of loadings and the factor covariance matrix and the covariance matrix of the idiosyncratic components. Now, of course, this thing has a reduced rank because there are only R factors here. Now, if we try to look at the case on the previous slide and fit that into this framework, well, what does our covariance matrix of the idiosyncratic components look like? Well, it has 1 on the diagonal and row off diagonal. So one way to write that could be, say, okay, I make it row everywhere, and then only on the diagonal, so the identity matrix, I add 1 minus row. And obviously you'll have the structure as we had on the previous slide. So if I then write out what this would be, so I have some predefined factors. I now have these correlated idiosyncratic components, so I can write it in these 2 parts. But then this part here with the row IP prime, well, it looks a tiny bit like this thing here. It also has some, here we have lambda, which is p times r. Here we have something p times 1. So maybe we could make an additional factor out of this. And in fact, if you rewrite it, so if you create a larger matrix, covariance matrix for the factor, so you add off diagonal element 0 and a diagonal element here of 1, and you split these part into the loadings, so you get the factor of 1s here times the square root of rho, and the same on this side, then we see that what we have now is actually a new factor structure where we have lambda tilde, which is this whole matrix. We have sigma f tilde, which is this whole matrix. And for sigma nu, we now have 1 minus rho times the identity, which is, of course, diagonal and definitely satisfies the weak dependence restriction. So we can come up with an additional factor, which of course we don't really explicitly have a factor, but this factor represents all the commonalities between your nu t, which satisfies these conditions, so it gives you this covariance matrix. Then this factor will in fact absorb the correlation between your idiosyncratic components that you had in your original model. So actually we've rewritten our factor model by including an additional factor. So what you may have in cases like this is when you do principal components and you do, for instance, look at the scree plot or look at information criteria, you would tend to find R+1 factors rather than R factors, because the dependence among the idiosyncratic components would get absorbed in this additional factor. Now, there are 2 ways to interpret that, I think. One is say, okay, well, this means that this case is ruled out and we cannot actually consistently estimate that model. But on the other hand, if we estimate a model with R+1 factors, this pretty much does the same job. So it captures all the features that you want to capture in that model. So it may not actually be a big problem if this would actually happen. And so therefore this assumption of no strong dependence among the idiosyncratic components is weaker actually than it seems, and it's more a way of actually defining a factor model, saying, well, everything that is common, that is strong, is a factor. And so even though we want to write it differently, we should not. And therefore, this is probably also part of the reasons why in practice you often find more factors, because there's probably dependence in idiosyncratic components that we might not think of economically as being a factor, but it's strong enough to actually get recognized as a common component. Now, another extension that we can make of factor models is to get dynamic factor models. Now, these are only relevant, of course, if you actually have observations over time. So far, everything we did was not explicit to have observations over time. Now we do assume that our t runs from 1 up to n as a time index. Well, what things you can do? Well, of course, you can allow for serial correlation. For instance, your factors or in your idiosyncratic error terms. Now, that is not so interesting. What is more interesting is that we can make the factor model itself dynamic. So we can let x not just depend on f at time t, but we can also let x depend on f at time t minus 1 or t minus 2 or up to t minus q. And this, of course, in a dynamic world makes very much sense. And this dynamic factor model is really the workhorse model of factor models in, for instance, macroeconomics, where this provides a very powerful extension. Now, there's one thing which is very interesting about these dynamic factor models, and that is we can rewrite a dynamic model as a static one. So suppose you have factors and you know that actually up to the qth lag they matter. What we can do then is define a new extended vector of factors, ft star, where we put not only ft in, but all of the lags. So you could write this dynamic structure as a static structure again. And that, of course, is really good news, because the fact that you can do that means that even though your true structure here might be dynamic, but you ignore it, what you will be estimating, for instance, doing your standard principal components plus creep plot or information criteria approach, you will actually be estimating this static model, which is still a correct representation of the data. And this is why, in fact, principal components still remain such a popular estimation technique. So even though we might truly have only r unique factors with q lags, we can write them as a static model with r times q plus 1 factors, so the contemporaneous one plus the q lags, and estimated by principal components. Now, of course, it would not be the most efficient you can do, because you're not using all the information that you have. I take a simple case where you have one factor only. Then if you define your vector of extended static factors, ft star, what we actually would know is that the first factor at time period t minus 1 should be the second factor at time period t, because the second factor is the lag of the first. So ideally, you would want to exploit that in the lag structure in estimation if you believe that that is indeed really the case. So how would we do that? Well, assume that you don't only have dynamic factors as an effect on x, but also within f you have dynamics. It seems very likely that if you're going to look at a dynamic model, actually the factor itself, in this case I'm doing it just for one, also is dynamic. And now what we can do is assume that actually the lag length here, s, and the lag length here on the previous slide, q, that these are equal. If they would not be equal, we can always add zero coefficients to make them equal. And then what we can do is, well, first, to do something that is should be familiar if you follow the time series analysis course. We can write the AR model here in companion form as a VL1. So the first line here represents our AR model, and the second up to q minus 1 line are just identities. So we have ft minus 1 should be equal to ft minus 1, and so on. And of course, there's no error term here because these are identities. The only error term is here in the first line. But if we do that, we can write it as a VAR1. Now, that allows us to use the so-called state space representation, where we write xt in its static form with the ft stars, but actually the ft stars, because those companion form here match exactly the ft stars that we defined to write our dynamic model as a static one. So we have found a dynamic representation for our extended factor model. So we can write this as a first order autoregressive state equation. And this model we can then estimate, and this model actually imposes all of the restrictions. By this, in this matrix here is phi star, you would actually impose this whole lower block, and you would only need to estimate these AR coefficients. Now, for this we can use the Kalman filter, which you might not be familiar with, so I'm not going to explain this here in details, as it actually fits better in a time series context. Let's just say what it does is essentially doing maximum likelihood estimation. So it imposes all the restrictions that we believe to be true. we do have to assume that our error terms are normally distributed. But if we do that, we can actually do very efficient estimation of such a dynamic model. And this is the second popular way to estimate factor models. Now note, I did it here for R is 1, but I can also do it for R larger than 1. Let me just very briefly describe how to do that. Well, it's the same idea. Suppose that we have dynamics now also in our idiosyncratic components. That again seems to be a natural thing to assume. And what we can then do is we can build a bigger vector even of not just the f's and the lags, but also of the idiosyncratic components and their lags. And we can say that this bigger extended factor vector, which I now call GT, is actually explaining XT. Now, the elements in this matrix A would be determined by the lambdas, the loadings of the factors. Well, and 0s and 1 to indicate where the right idiosyncratic components actually come in. And we also have the dynamic equation, which explains how the unobserved variable GT, how it evolves. And it has a matrix B, which is now a combination of the dynamic structure in the factors and the dynamic structure in the idiosyncratic components. And this again is something that we can actually estimate by maximum likelihood very efficiently. So this makes sense to consider this model, but of course there are also disadvantages. And the major disadvantage is that you have to specify the full model correctly, including Gaussian error terms. Now it will still work reasonably well if you don't have Gaussian error terms, but something which is not too far off. But you also have to get the dynamic structure right. So you have to get all the dynamics right, and if you miss some, then you will have a misspecified model. On the other hand, the brute force principal components estimation, the static version, only requires the number of static factors. And well, for that we have methods to determine that, and as long as you're not too far off, then, well, you get a reasonable estimate. So principal components tends to be much more robust than the dynamic parametric maximum likelihood approach. Now, obviously, there are tons of other methods you can have a look at to estimate factor models, and in the literature that is posted on Canvas, there are several links to references which discuss alternative estimation, including sort of hybrid forms where you go into a bit of the middle. Now, I'm going to focus mostly on principal components in the remainder because it's such a simple and effective method to estimate factor models. But keep in mind that there are indeed actually alternatives for estimation here. Then in the next lecture, I will discuss the intuition behind the asymptotic analysis of factor models.